Welcome everyone to another live session for the online class. It's a new year, new things happening in astronomy, and I'm ready for your questions on any topic.
All right, our first question from a live, this is from a previous session from a live viewer. That was an interesting question I wanted to make sure we got to was, can you talk about the latest information about type 1a supernova, and then how many subtypes are there and what are the differences?
Right, so for just to back off to the general categorization of supernovae, there are two fundamental types of supernovae, type 2 and type 1. Type 2 are extremely massive single stars that die explosively at the end of their lives. So they're typically stars which start their lives with about 8 times the mass of the sun or greater, and they will die as a supernova and typically leave behind, usually a black hole. Sometimes the detonation can be perfect and nothing is left over, and possibly a neutron star. So those are, extremely powerful events. Luminosities maybe 1 billion times that of the sun. The type 1As are supernovae that are part of binary systems of stars, where the mass transfer from the companion star pushes the other star over the mass limit, the Chandrasekhar limit, and causes a detonation as a supernova. The difference between a supernova and an isolated star and in a binary system is the isolated stars have all different masses, and the luminosities of those explosions, their brightnesses, vary enormously by more than an order of magnitude, 2 orders of magnitude, factor of 100. But in a type 1A system, because the detonation is caused essentially by fuel sort of being spooned on at a very slow and steady rate from a companion star, they detonate at a very particular mass, and so the luminosity of the explosion is quite well regulated. And empirically or observationally, the range of brightness of a type 1 supernova, and these are type 1A classically, is only 15%. And that is the reason why type 1A supernovae have been so useful in cosmology, because these are like standard explosions, standard bombs that we can see out to enormous distances in the universe, 5, 8, 9 billion light years away. And because we know the luminosity, if you have a cosmic expansion model, you know their distance, and so you can talk about different world models, different expansion histories of the universe. So type 1A supernovae have been used for a couple of decades now to talk about the expansion history of the universe. But as people started to gather more data on supernovae, these simple binary distinction between 1 and 2 got more complicated. So there are now type 1As, type 1Bs, type 1Cs. I think there's E and F as well. And those different letter subdivisions reflect different chemistry in the parent star that explodes and in the expanding gaseous envelope, which is enriched with heavy elements, of course, due to the explosion itself. And I literally can't remember all the spectroscopic distinctions between the 1B, the 1C, the D, E, and F, and so on. But these are important for people who want to understand the chemistry of the universe and how it results, and how it depends on the chemistry of the star that exploded. But for cosmological purposes, the 1As are still the gold standard for measuring the expansion rate of the universe.
All right, the next question is from, from Lynn, who's on with us live, who asks, can you explain what causes the moon to look really large, like the photos where the moon fills the horizon down a long stretch of road? Is this a supermoon? How can we see this effect?
So the effect you're talking about is not the same as a supermoon. There are months when there are 3 when you get the double moon cycle just by the timing with the calendar. The diffraction, or the sort of distortion of the moon's apparent size, is something that's been commented on a number of times. There are some scholarly articles that actually deal with this, because of course the truth is that if you measure the angular diameter of the moon, which is about 30 arc minutes or half a degree, as it moves across the sky, it changes not very much at all. There is a small distortion that happens because of refraction when it's low on the horizon. So when it's low on the horizon, it is being refracted by the light path through the thick part of the atmosphere, and that refraction depends very sensitively on the angle. And so the moon does amplify slightly in its angular size very close to the horizon. It also reddens, of course, because you're looking through much more path length of the atmosphere. So you can see this red and apparently slightly bloated moon hanging low on the horizon. And that's a real effect, and it's measurable, but it's actually quite a small effect. It's I think less than 10% in the angular size. Any other effects, such as the way it appears big when it's above the horizon or high overhead or so on, these are perceptual things. When your eye is trying to measure or register the angular size of something bright in the sky, and it's untethered by any other object, by horizon or any other reference, then because it's untethered, the eye in the perception of the brain does all sorts of different things, and it varies from person to person. So a lot of the perceptions that people have that the moon angular size is changing or varies with position on the sky are purely psychological effects. They're not even entirely physiological, and they're not physical at all.
All right, the next question from Leilani, who's on at this live, asks, are the tidal forces of Earth causing the moon to drift away from it?
Yes, that's a good question, because there is a direct interaction between the Earth and the moon. So obviously the moon orbits the Earth, and it has this 28 and a half day orbital period. But the moon, that interaction or that gravitational tug between the Earth and moon is very strong. And because the moon is a large object in a relatively close orbit, you can just use the inverse square law of gravity to see that the gravitational force of the Earth, manifested about the center of mass of the Earth, is higher on the near side of the moon than it is on the far side. And that's a significant amount. I mean, it's a small percentage, but it's a significant amount. And so that is a tidal force, the difference in the force the Earth exerts on the front side of the moon and the back side of the moon. That has two effects. The first of the effects is obvious to anyone who looks at the moon more than occasionally, which is we only ever see the same side of the moon. There are other satellites and moons of planets in the solar system where those moons are spinning or orbiting. The Earth is obviously spinning on its axis as it orbits the sun. So many objects form with angular momentum, and they have their own spin, which seems independent of the object they're orbiting. But in the case of the Earth and the moon, the proximity and the large size and mass of the moon relative to the Earth means that it's become tidally locked. So that tidal force is gradually, over time after formation, produced a situation where the moon keeps one face towards the Earth due to this tidal force. There's also a slight transfer of angular momentum. So what happens also because of that tidal force is that the Earth is very slightly being slowed down in its spin. And that angular momentum, which is also corresponding to an amount of energy, is being translated into a slight increase in the distance between the Earth and the moon over time. And this is imperceptible, of course. I think the number is that the moon gets about 4 centimeters further away from the Earth every year. It's obviously a very small amount, but it's not a trivial amount. It's not a negligible amount. And I think the corresponding effect on the Earth's spin is that the Earth's day gets about 1/millionth of a second longer every year. So these tidal forces and interactions do have a real effect, and they do mean that the moon, is moving away from us. People playing this back in time have found very significant differences played back over hundreds of millions or billions of years, but it's hard to measure that far back in time. But we can measure what's happening right now and project it into the future, and the moon is indeed receding. And if you play that out into the very far future, hundreds of millions or even billions of years, there will become a point where the moon recedes so far from the Earth that it is no longer tidally locked. And so that seeing the same face of the moon will not be true forever.
All right, so Camilo Prieto 34 and Annie Bachman, hopefully those are answers to your questions because they asked related questions. I just want to make sure to call them out so they're sure that they,
Okay.
You know, we did get to it. Just I'm not going to call them out separately. So the next question from a live viewer is from Nightingale, who asks, other than stellar parallax, are there other or newer methods being used to determine the distances of stars?
There are other methods. Many of them are traditional, however. The parallax method has had new life. Remember that for determining stellar distance, the parallax method is the most direct because it's based on simple geometry. So to review, the stellar parallax distance measurement just uses the baseline, sets up a little triangle where the base of the triangle is the diameter of the Earth orbiting the Sun, so twice the Earth-Sun distance, so between two observations 6 months apart, and then you observe the star that you're trying to measure the distance to, and the skinny little angle that those two sight lines make with the star is the parallax angle. It's a displacement of angle seen observing that star one time and then 6 months later. So that's parallax, and that angle is typically very small. It's less than an arc second, so thousands of times less than the angular diameter of the moon. And because of because of satellites and space observatories, first the Hipparchus mission and more recently the Gaia mission, we've been able to measure parallax. With Hipparchus, it was for a couple 100,000 stars, and with Gaia, it's for millions of stars, 100 million actually, very accurately. So parallax, is the traditional method, and it's got new life because of these very powerful missions, especially Gaia, European mission from the European Space Agency, that has been able to measure distances by this very direct method based on geometry to hundreds of millions of stars. So that's not a significant fraction of the entire Milky Way, but it's more than just the solar neighborhood. Beyond that, the methods of measuring stellar distance are much more indirect because they reference stellar properties. So the archetypal stellar property method was the Cepheid variable star. So these are luminous, late-stage stars that have periodic pulsations, and the pulsation period is correlated for astrophysical reasons with their luminosity. So if you can measure the pulsation period of a Cepheid, and RLI is another form of variable star where you can do this, you can predict what the luminosity is, and if then you measure the apparent brightness, those two things are related by the inverse square law of light propagation, and you measure the distance. So Cepheid variables were used famously by Hubble to measure the distance to Andromeda galaxy in the late 1920s, and then in the Hubble Space Telescope Key project in the 1980s, late 80s through the 90s, was used to measure the distances of hundreds of neighboring galaxies to the Milky Way by this very direct method. So Cepheids have also gained new light by space observatories and measuring the distance to hundreds of galaxies. It's a very mature, well understood astrophysical technique. And then, of course, as already mentioned, supernovae, type 1a supernovae, is eventually a stellar property. It's the death of a star with a very well-regulated luminosity, which can also be used to indicate distance. And that it gives the largest reach of any kind of distance indicator, because that takes you out well beyond the nearby galaxies to large fractions of the size of the universe.
All right, and I just want to point out to Rami that answered his question about Cepheid variables as well. Our next question is from a live viewer, Ag Arms, who asks, what are you most excited about in the search for life outside the solar system? Does TRAPPIST-1 seem the most likely place we know of to look for life?
TRAPPIST-1 is definitely interesting because it's a relatively nearby system, a few dozen light years. So it's one of the best. Some people still are very excited about Proxima Centauri, which has very likely one Earth-like planet and possibly a second, and that's of course only 4 and a bit light years away. So that's very close, and it's a very bright star, so you can gather a lot of information. So I would say there are about half a dozen relatively nearby sun-like stars which have known Earth-like or super-Earth planets around them, detected either initially by the Doppler method or subsequently by the eclipse method, the transit method using Kepler. Actually, sorry, these are not from Kepler, because Kepler is looking at one particular area of sky, and they tend to be more distant stars. Kepler has not really given us any nearby candidates to look for life on a planet. These have come from other surveys. So these handful, maybe 6 or 7 total targets, are compelling targets to look for life. And the experiment you're trying to do next, is, of course, the very difficult experiment of looking for reflected light from that planet, the Earth-like planet, or potentially the starlight from its host star filtering through the atmosphere of that planet and imprinting absorption, whereby you're looking for the telltale signs of biological alteration of an atmosphere, which would be, as in the case of the Earth, ozone and oxygen, methane, water vapor, of course, and possibly some other molecules. So that experiment, or the blotting out of the light of the star and looking at the reflected light of the few 100 million times fainter planet and smearing that into a spectrum, those experiments are on the edge of being possible. They're definitely possible when we have 20 and 30 meter telescopes, and people are working really hard to try and do them with the sort of 10 to 12 meter telescopes we have right now. There are also space missions which could do this, but not for, well, the James Webb can do a little bit of this work. It wasn't really designed for it. There are optimized space missions to do it in 7 to 8 years. So it's a good bet that within a decade, one of these approaches will succeed, and we'll have measured the atmospheric alteration by biology on a nearby exoplanet. That's an incredibly exciting prospect.
All right. Next question is from William, who's on with us live, who asks, how can we be certain that a visible light event or object is associated with a specific gravity wave event? Is it only based on timing, or are there other criteria that link them?
So the gravity waves is a non-electromagnetic signal. It's completely different from all the information we've had in the universe until 2 years ago. And it's been a challenge to associate the gravity wave events so far, just a handful, with any direct astronomical event with electromagnetic radiation. And it's essentially not been possible. For the best of these gravity wave events, when it's detected at a third station beyond the 2 that LIGO has, you localize the source to something like 30 or 40 degrees in the sky. That's a huge chunk of real estate, of space, and thousands or millions of targets. So how can you and since the reach of gravity wave detectors is 1 or 1.5 billion light years, that's the distance to a couple of the first emerging black hole events, there's so many possible places these events could come from that you can't localize it. So at the moment, gravity waves can't be localized. They can't be pinpointed to a place on the sky or single galaxy far away. And changing that situation is going to take a couple more years. You need more detectors, basically, because you're trying to triangulate a position from 2 points, which is very crude, or possibly a third point using the European gravitational wave detector. There are detectors that will come online in the next 2 years in Japan and India. If you get a gravity wave detection, merging black holes, with 5 of these gravity wave detectors, then you're starting to approach a pinpointing that might let large telescopes see where that event came from. But otherwise, it's hard. The sidebar on this is, of course, that great excitement last year came when there were emerging neutron star that produced a gravitational wave event, and in that case also generated a gamma ray burst and a large amount of electromagnetic radiation across the spectrum. It was detected by, in the end, I think more than 60 telescopes on the Earth. So for neutron star mergers, that's the place where we know how to localize the event, because electromagnetic radiation also results from that merger. But for merging black holes, that's electromagnetically quiet. And so until we have more gravity wave machines online, we're not going to be able to localize those events at all. We can say how far away they are, We can say what the luminosity is in gravity waves. We can say what the masses of the two objects that combined to make that event were, but we can't identify a particular source galaxy.
All right, the next question is from Angelo Moro, who's on with us live, who asks, can you please explain the term naked singularities and also explain how supermassive black holes form?
So the term is sort of two separate questions. So the question of what is a naked singularity? So in the theory of black holes that derives, of course, originally from the theory of general relativity. So Einstein's theory predicts black holes, even though Einstein himself doubted their reality or their existence. Karl Schwarzschild, around the time of Einstein, solved general relativity equations and inferred the existence of something that had a singularity. In other words, it was a gravitational collapse where, in principle, if you solve the equations, the mass and the density were infinite at the center. And so that's the definition of a singularity. It's where a number blows up or a physical quantity blows up. It's essentially unphysical. Obviously, there's no such thing as infinite mass density. That doesn't mean anything. But that's what the theory of black holes predicts. The theory of black holes also predicts an imaginary surface. It's not a physical surface, called an event horizon, which corresponds to the region within which nothing can escape, no information, no light, no particle, no information of any kind. And so in the simple theory of black holes have a singularity, which is this infinity, this sort of physical problem at the center, infinite mass density, infinite density. And then, but everything that goes on there is shielded by this event horizon, which just prevents us from seeing inside. The speculation right from the beginning of the theory of the black holes at the era of Stephen Hawking and Roger Penrose in the 1970s is that perhaps naked singularities exist. Perhaps it's possible in some physical circumstances to have a black hole that's not shielded by an event horizon, and that's what a naked singularity would be. And various singularity theorems were developed. This is the work of Hawking and Penrose in the 1970s that essentially argued that naked singularities should not exist. They should always be shielded by an event horizon. So a naked singularity is something that's conceptually possible and it's mathematically possible, but the theory suggests that we would never actually see such a thing. And in terms of the black holes that we know of in the universe, most of which are nearby dead stars, there's no sign that a naked singularity exists. We've seen indications now of event horizons, so we think they exist. So it's likely that nature doesn't make naked singularities. And the second part of the question, which is sort of a different question, was about the existence of supermassive black holes.
Yeah, how supermassive black holes form.
Oh, so supermassive, the black hole spectrum is very broad. The low mass black holes from the death of massive stars kick in around 8 or 10 times the mass of the sun. And the most massive black holes we've ever seen in the centers of distant galaxies are something like 10, 20, maybe even 30 billion times the mass of the sun. So black holes span a range of 1 billion, essentially, in mass, which is a phenomenal range. And we found examples almost everywhere in between in that spectrum. The most massive black holes form by mergers and acquisitions, just the way sort of industry and corporate world works. Smaller things merge together to form bigger things. So the speculation, because we haven't actually watched this process happen over time, is that there are seed black holes in the early universe, and these are very likely the central regions of galaxies where gravitational collapse happened very quickly. And so essentially a supermassive star collapsed to form a pretty beefy black hole. That's more beefy than the black holes we see in the nearby universe, which tend to be 8, 10, 15 times the mass of the sun. These could possibly go up to 50, 100, or a few hundred times the mass of the sun. So in the very rapid gravitational collapse of sort of small proto-galaxies, if you like, in the early universe, you have a population of seed black holes, or things that are tens up to a few hundred times the mass of the sun, possibly 1,000 times the mass of the sun. And they live at the center of what would be dwarf galaxies then. In that early dense universe, those galaxies merge and combine. And when those dwarf or early primordial galaxies combine, their black holes just come together and merge and add. They release some gravitational radiation. So the arithmetic of black hole mergers is that A plus B is not simply A plus B, it's A plus B minus the gravitational radiation that's radiated. But the masses are obviously increasing. And so in our understanding of the evolving universe, as small galaxies merge to form bigger galaxies, and eventually something like the Milky Way or a giant elliptical galaxy, the black holes within them are also merging, and their masses are growing additively. But in addition, they're also feeding on material, gas, and even whole stars in the center of these galaxies. And then initially, in the first part of the universe, there's a lot of gas available. It falls into the galaxies from outside and then works its way to the center, or it's just available within the galaxy and gets to the central region where the black hole can consume it. So there's a lot of feeding and fueling going on of black holes, which also grows them. So by mergers and by feeding on gas and available material, including whole stars in the centers of galaxies, these black holes grow. And the challenge, actually, one of the challenges, it's not a particular challenge to explain a 10 million or billion solar mass black hole in the present day universe, because you've had 13.8 billion years to build them. But the challenge is that some high redshift observations have shown billion solar mass black holes in the center of distant galaxies, quasars, that are seen very far back in the universe, within a billion years of the Big Bang, and getting from a few hundred solar masses, the seed black hole mass, up to a billion solar masses in less than a billion years, maybe even in as little as a few hundred million years. That's extremely challenging. Theorists think it can happen, or they think they now know how it can happen, but that's actually become one of the biggest challenges in cosmology to explain that.
All right, our next question is from a live viewer, Tarun Kumar, who says, I have heard that the Earth is moving away from the sun a little bit each year. Will that change whether the Earth is within the habitable zone?
So yes, in a more reduced form than the Earth-Moon interaction, where the tidal locking and the tidal forces are stronger, and so that Earth-Moon interaction, which is changing the Earth's spin rate slightly and causing the Moon to recede from the Earth, that's happening also with the Earth and the Sun. The act of gravitational interaction and the sort of coupling between the Earth and the Sun is very, very, very slightly changing the Sun's spin rate, its angular momentum, and increasing very, very, very slightly the Earth's distance. This is a tiny effect. It's unmeasurable, essentially. It's just a prediction from gravity theory. And it will not actually take the Earth out of I think I've seen the numbers on this. It will not take the Earth out of its habitable zone before the Sun dies in 4.5 to 5 billion years. So the Earth will become uninhabitable due to the demise or late stage changes of the Sun before it moves out of the habitable zone due to this gravitational effect.
All right, so we have two questions related to the Oort cloud. So the first question is, how would Voyager 1, any of our distant space probes, pass through the Oort cloud safely? And then somebody else would like to know just what is the Oort cloud? So
to answer the second question first, what is the Oort cloud? The Oort cloud, I have to say, is a hypothetical entity in astronomy. It's the parent population of the comets that visit us episodically in the inner solar system. So when you observe comets, that not all comets come past the Earth's orbit and approach the sun. Some of them exist in the outer solar system and come into the outer solar system and then recede to large distances. But if you take the totality of comets that are visible from the Earth, traveling through or near the inner solar system, and their orbits are so extremely elliptical, and Kepler's law says that for the very short time that they whip through the inner solar system, months or typically a few years, they must spend a vast amount of time at very large distances from the sun in their highly elliptical orbits. And so the inference is you're only seeing a tiny fraction of the population. So just because of simple orbital mechanics, the comets we see must be representatives of a very large population of comets that spend almost all their time, the vast majority of their time, at very large distances from the sun. Those large distances are tens of thousands up to 100,000 astronomical units. And that's a significant fraction of the distance to the next star. So this Oort cloud is the hypothetical repository of comets in their sort of deep frozen state in the large part of their orbital time, which is spent far from the sun. Now, because they're so far away, and because comets are small, 5, 10 kilometers across, and because they're not active, because they're far from the sun, so they're just dead rocks or rocky, icy balls, they're unobservable. So no one's ever observed a comet out in the Oort cloud, the repository that leads to the occasional visitors we get in the inner solar system. And in that sense, it's a prediction. It's a hypothetical construct. Logically, it should exist. And it could indeed contain an enormous number of comets. The round number that people talk about is like 1 trillion comets. So the totality of the Oort cloud is 1 trillion comets that are all small, dark, inactive, spending most of their time at distances of tens of thousands of astronomical units, and as yet unobserved. That's the Oort cloud. And the second question was about how can we observe it? I mean, I didn't do this. I did the second question first, the definition.
Yeah, so the second one is how will our interstellar, or how would our most distant space probes make it through the Oort cloud? So,
so we're just predicting the properties of the Oort cloud, but and so I've put numbers on it. So for the other question, how can our spacecraft travel through the Oort cloud? It sounds like with 1 trillion comets, even if they're physically small, that could present some hazard for a spacecraft traveling in the outer solar system. But not really, because if you think about how empty space is, that's still, it's an enormous volume. So remember, this is a spherical volume where the radius is, let's just say, 30 or 50,000 astronomical units, which is trillions and trillions of miles. And you have things that are a few miles across. And even though you have 1 trillion of them, in the volume they occupy a tiny, tiny, tiny fraction of the volume. So the odds of a spacecraft intercepting one, certainly colliding with one, are negligible, or even getting close to a comet are very low. So because the solar system is in almost entirely empty space, and the Oort cloud is almost entirely empty space, so diffuse, it's not a hazard for spacecraft at all. So NASA engineers, when they were realizing we had space probes heading out into the Oort cloud, they didn't worry about this at all. They knew it was unlikely to be a problem.
All right, the next question is from Muzahir, who's on with us live, who asks, what caused the expansion of the universe to slow down after cosmological inflation?
Right, so it's a good question. The inflationary model, or the Big Bang model with the addition of inflation, posits that the universe underwent an exponential phase of expansion from a tiny, tiny state, smaller than a proton, to an ending point that was, meters across. The number is a little indeterminate, but it's not a very vast number and it's not a very tiny number. It's intermediate. And then the universe essentially went through a phase transition where the energy from the inflationary field gets converted back into energy in the universe that can then form matter and antimatter initially, and then all the radiation and matter that we see. So the universe has these different stages. It has this exponential stage of inflation, which occupies a time frame from about 10 to the minus 36 or 35 seconds after the Big Bang to about 10 to the minus 32 or 33 seconds after the Big Bang. Numbers are a little uncertain, and these are all incredibly tiny fractions of a second. And then the universe transitions to a more leisurely Hubble expansion. So the inflation is driven by what's called the inflaton field, which is whatever field is responsible for this exponential expansion of space-time, which we think emerged out of the the breakage between the merger of the four forces of nature, the end of the grand unified theory era. That drove the exponential expansion. And after that transition was over, the universe just resumed a more steady expansion, decelerated steadily by the amount of matter and then mostly dark matter in the universe. The exit to inflation is still a matter for theoretical debate. Observations can't really address it. So the time, how much the universe expands exponentially during inflation, how it exits from inflation into this more leisurely, linear or decelerating expansion is still up for debate, and people essentially don't know the answer. Thereafter, though, we do know how to describe the universe very well. For whatever its inflation, whatever its expansion rate was at the end of inflation, its subsequent expansion rate is changing according to the amount of dark energy and dark matter in the universe. And initially, in the first 5 or 6 billion years, the expansion rate is simply decelerating due to the matter and normal matter and dark matter in the universe. Dark energy gradually becomes more important, and so for the last part of the universe's expansion, it has been accelerating.
The next question from our live viewer asks, basically, can you please talk a little bit about supernova 1987A?
So supernova 1987A was a great gift to astronomy all those years ago. That's 30 years ago, a long time ago. I can remember it, though. I was a young professional, just started as faculty member that same year, actually. So 1987A, in the typology of supernovae, I talked about the difference between the binary star supernovae, the type 1As that are used as distance indicators. Supernova 1987A was a type 2 supernova. It was a single massive star that detonated. The reason why it was special is because the supernova rate in any particular galaxy is very low. Only the most massive stars die as supernovae, and those massive stars are very rare. They're a tiny fraction of all stars in any galaxy. And so the odds of seeing a massive star when it's such a minority population go off in any given year are really low. And if you work it out for a big galaxy like the Milky Way, the supernova rate should be about 1 every 50 to 100 years, maybe a little more. So you'd have to be staring at a galaxy like the Milky Way for a century to see a single supernova go off. As we know, it's been over 400 years since there was a supernova in our galaxy. Kepler's supernova 1604 is the last one. So we're well overdue. The timing of supernovae is governed by Poisson statistics. It's hard to predict, and so that's not bizarre or strange that you have to wait 400 years. But that gives a sense of the problem, that you've got to be very lucky to have a supernova go off that you can observe. 1987A was a supernova in the Large Magellanic Clouds, one of our 2 nearest neighbor galaxies. And so while it's not as good as a Milky Way supernova, which could have been 5,000 or 10,000 light years away, it was a little over 100,000 light years away, which is right on our doorstep. It's right in our backyard. So that supernova, when it went off, was the closest we've ever got to observe a supernova. And it was the brightest supernova since Kepler's supernova of 1604. So it was a really major event. And it was also the first supernova to go off in the modern electronic age of astronomy, where we had electronic detectors, CCDs. Every telescope really on Earth could participate in observing it. It was actually too bright for the large telescopes to observe for a few weeks. It was bright enough to be observed by the naked eye, of course. It became a bright star in the night sky for a few weeks. And that was actually too bright for a big telescope. You'd actually have to half close the mirrors to be able to observe it without melting the detector. So it was an incredible opportunity because we knew about it right away as soon as it went off, because we had the generation of modern telescopes with electronic detectors, all of which could be turned towards it. We learned more about how stars die from that one event than from any other. And there's been nothing since to rival it. And also, we've got to play it out over decades. So the Hubble Space Telescope over time, and then ground-based telescopes, have observed these exquisite light echoes from 1987A, which is the blast wave went out from the supernova at nearly light speed, relativistic speed, and as that blast wave moved out through three-dimensional space like a spherical blast wave, it hit stationary gas in front of and behind the supernova, and that gas lights up, and then with a travel time delay corresponding to how far away that gas was, we see that gas brightening with telescopes, and that's called a light echo. So we've watched over decades now the light echoes from the supernova as its blast wave plows into surrounding material, and we've learned more about supernova, the energetics of supernova from that. We've learned about the chemistry of supernovae, about how heavy elements are created and how many heavy elements are created. Really an enormous amount of information. And, entire research symposia have been dedicated to 1987A, more than a handful, and entire books have been written about it, technical scholarly articles and books written about 1987A. So it was really an extraordinary event.
All right, I'm going to jump ahead a little bit because there are some questions that have come in recently that are similar to, that are different than ones we've heard before. So I'm just going to jump around a little bit so I want to let our viewers know. So I want to get to two questions from one of our participants, Guillermo, who is interested in how the Earth is visible to other observers from who might be looking at us using, say, a transit method or a Doppler method of exoplanet detection on us. So how far would the Earth be detectable using transit photometry, and how much does the Earth affect the sun's spectrum, and where else in the Milky Way would we be observable from?
So it's a sort of reverse experiment. We're doing the experiment of detecting Earth-like planets around sun-like stars. And from Kepler, I think the body count of Earth or super-Earth planets is now over 1,000. And probably half of that, or maybe 300 or 400 of those, are truly Earth-like, like within a factor of, within 30 or 50% of Earth mass or Earth size. So we have hundreds of Earth-like planets from Kepler. Those are at distances of 1,000, sometimes several thousand light years. So logically, if we have a 1-meter telescope that could detect an Earth-like planet around a star 1,000 light years away, then some other civilization on a planet around a star 1,000 light years away with that same technology could detect us. Just reverse the logic. So we are eminently observable by any civilization that has telescope technology and detectors of the same kind that we do. And that's only getting better. So as our detections get more sophisticated, presumably our grasp or the grasp of some other civilization to detecting Earths gets even further away. And there are a lot of Earth-like planets within 1,000 light years of the sun, tens, maybe hundreds of thousands, maybe millions. So it's an enormous amount of Earth-like real estate. So again, if any civilization is able to do this experiment, they're observing a lot of planets like ours.
All right, the next question is from Batsal, who asks, what is the farthest celestial body we have received light from?
So there are galaxies that have been, distant galaxies that have been published in the last year, actually. And I don't remember their names. They have unmemorizable names that are just a series of numbers and letters. But distant galaxy surveys and also high redshift quasars, they're all in the same vicinity. So these most distant objects that we've detected with our telescopes are about 13.4 billion light years away. So, or rather, their light has been traveling for 13.4 billion years. I'm going to make a distinction about that in a minute. And so the universe's age is 13.8 billion years. And so you can see that we have seen back with telescopes light from distant galaxies that's been traveling for over 90% of the age of the universe. I think the actual highest number is like 94, close to 95% of the age of the universe. That's really phenomenal. So we've seen back 95% of the way to the Big Bang with telescopes, these distant galaxies. The distinction on distance is that because the universe was expanding faster than the speed of light for a lot of the first part of its expansion history, the distance to these galaxies is more than the number you would expect. You might expect a galaxy seen 13.4 billion years ago to be 13.4 billion light years away. But that's not true. The number is much higher. It's a couple of times higher, 2 or 3 times higher, because of the superluminal expansion of the universe. I don't remember the exact number, but the most distant objects we're seeing, those ones I've just referred to, are at distances of over 30 billion light years, maybe 35 billion light years away. So those are the most distant objects. Could we see even further than that? It's going to get harder because at some point we run out of light. Already these distant galaxies are at redshifts of close to 10, so their light has been shifted to the red by an order of magnitude, which means as we observe that light, it's been moved out of the visible spectrum into the infrared spectrum, which makes it harder to observe, actually. That's a messy part of the spectrum for detecting distant astronomical objects. So the galaxies have been made fainter and redder by the expansion, and also, at some point, there weren't any galaxies. We're reaching very close to what are called the dark ages, that period of time which may have lasted 200 million years between when matter first became stable, normal stable atoms, and gravity exerted enough of a grip for the first stars and galaxies to form. So the universe was dark until that happened. And there's no way with telescopes we're going to see the dark ages. All we can do is reach back towards the dark ages. And these most distant objects suggest that we're getting pretty close to the first galaxies and stars.
All right. The next question from our online viewers is about comets and meteorites. Scientists have long believed that comets and a type of meteorite called carbonaceous chondrites were the source of Earth's early volatile elements, water, and organic material. What's the latest information that we have on that, or the latest evidence?
Right. So the Earth, there was a theory called the late veneer theory, which was trying to explain where a lot of the organic carbon-rich material, and especially the water on the Earth, came from. And the late veneer theory held that after the Earth formed, which didn't take very long, probably took 30 to 50 million years after the formation of the solar system. So really, that's very short. That's within the first 1% of the history of the solar system. That the Earth may have been initially dry, but the sort of rocky and icy material that slammed into it as the solar nebula was clearing out of gas was what added the volatile material, frozen gases, and frozen water that made the Earth's oceans. And carbonaceous chondrites are meteorites that do have a lot of carbonaceous material. And of course, comets, we know, have a lot of frozen water and also carbon-rich material. So meteorites and comets are plausible sources for the Earth's water. The problem with this story, however, is that the isotopic ratio of normal stable oxygen to its radioactive isotope partners in the Earth's oceans is different from the isotopic ratio of water that's been measured in the couple of comets that have been measured so far. So the story of comets depositing the water for the Earth's oceans doesn't quite hang together. Now, that's small number statistics, and nobody's willing to call it a super problem at the moment, but it's definitely a fly in the ointment for this model. But in principle, yes, the deposition of small bodies onto the Earth soon after it formed provided both the liquid that life depends on and a lot of the organic material that life is based on.
All right, the next question is, what are the conditions under which a cloud of dust and other matter collapses to form a star?
So star formation is kind of a messy process. If you look in a textbook or a diagram online, it's presented as a spherical or a quasi-spherical gas cloud, maybe a sort of irregular but close to spherical gas cloud that somehow becomes gravitationally unstable and just shrinks down into a star. That's really not how it happens. Star formation happens chaotically in very irregular and chaotically shaped regions of gas and dust. And we can see these regions in space. If you look at any of the nebulae, not to the naked eye, you can't see enough detail, but in the Hubble images, say, you can just see how crazy and chaotic these regions are. Also, stars do not form singly. The sun formed as part of a group of stars, and most stars form in clusters or groups, and sometimes even very large aggregations. So you're not just forming one star, you're forming a lot of stars at the same time. Those stars also have random velocities, and the interactions between them sometimes kick young stars out of the system. Those stars are moving fast enough that they plow through the surrounding gas and disrupt it. It's a really kind of messy situation. So we think we know how stars form, but the details have really only been revealed by computer simulations because it's so chaotic. And there's not a lot of symmetry about this process too. There's a conservation of angular momentum that does mean that however irregular a cloud was to start with, it's most likely to turn into something like a pancake shape, where there's a spin axis or an angular momentum axis, and it will collapse perpendicular to that axis. And that's what leads to a disk, that's what leads to planets, and that's what leads to the fact that there's a spinning star at the center of each solar system.
All right, the next question is from a live viewer, Beatrix, who asks, I recently learned the sky on Pluto is blue like Earth's. What color are the skies on other planets like Mars?
So Pluto has a very thin atmosphere, but yes, I've heard that too. It is that there's enough scattering from very small particulates that it would show that signature of blue. Also, Uranus and Neptune, you can see this in images on the web. Those are often color enhanced, so the true coloration of Uranus and Neptune is very subtle. It's just very, very pale blue, almost white gray. And in that case, it's a slightly different reason. It is also, in that case, because of methane, because of particular gases in those atmospheres. Jupiter and Saturn, when you look at the colors, natural color images, not quite as red and yellow and orange as you might see in the enhanced Hubble Hubble photos or spacecraft photos. But it is very definitely sort of dingy, yellowy brown, and that's from aerosols. That's from sulfur compounds in the atmosphere, nitrous oxide, and so on. So those are real colors that reflect the chemical composition of the atmosphere. The Martian atmosphere, it actually doesn't really have much color because, the redness of you're looking at Mars through the atmosphere, very, very thin atmosphere, and the redness of Mars is due to the rocks on Mars, due to the oxidation and the iron in those rocks. The Martian atmosphere is made of carbon dioxide, and carbon dioxide is colorless. So Mars doesn't really have a color for its atmosphere. Venus, similar to the giant planets, has some of those similar ingredients, has a lot of carbon dioxide, which would be colorless on its own, but also has some rather toxic compounds too. Has sulfur dioxide, there's sort of sulfuric acid in the Venusian atmosphere, there's some methane, and so the pale color, again, reflects those different gases. So the colors are meaningful. The trick is that when you look online or look for photos of planets in the solar system, it's very hard to find true color photos. You're almost always looking at enhanced colors, which are quite garish and extreme, and they're not really physically correct.
All right, our next question is from Kenneth, who asks, why doesn't the Earth have rings like Saturn?
Well, it's a good question. All the giant planets have ring systems. So Saturn's, of course, ring system has been observed since the telescope was invented. And through spacecraft, through the Voyager and Pioneer series, the other three giant planets were revealed to have ring systems. You had to get closer to see that. It's not easily visible with a telescope, although it has been observed with telescopes now, and especially the Hubble. So these giant planets have ring systems, and the rings in these cases are essentially failed moons. All the giant planets have moons. The Jupiter and Saturn have over 50 moons each, I think, and the Uranus and Neptune have over a dozen moons each, going down to pretty small moonlets. And the amount of material left over from the formation of that large number of moons disperses into rings along their orbits. Some of that material is cleared out or evaporates or disperses over time, so the rings probably will eventually go away. But smaller planets, terrestrial planets, just don't tend to have enough material left over to form a ring system. It's conceivable that there was a very subtle, mild ring system around the Earth or other inner planets. It's also likely that there were small moonlets that have since dispersed or moved away or interacted and been tossed out of the system. But the small planets just don't have enough material left over to make rings.
All right, our next question from a live viewer, and this is going to have to be the last one because we are almost out of time, is what evidence could we look for that would support the theory of wormholes?
That's a challenge because a wormhole is again a theoretical concept it's possible. I wouldn't say it's directly predicted out of general relativity, because general relativity can accommodate anything that gravity can do, but the space-time we live in is kind of simple space-time. It's mostly flat space-time where the only curvature is caused by individual compact objects. We don't live in a sort of convoluted world of space-time undulating and being topologically complex in general. It's mostly smooth, flat, with the exception of these compact objects. Well, the wormhole concept is imagine a connection in space where space from one region is pinched together with space from a different physical region, and the tunneling between them would amount to a wormhole if you just sort of interconnect these regions, these very different regions of space-time. So that is possible in theory. You're not violating general relativity to hypothesize that a wormhole exists, that interconnection regions of space-time exist, where possibly and hypothetically you could travel between them. But having it as a possibility in a theory where you don't violate relativity to say that they might exist is very different from saying that they actually do exist and where you would find them. And the truth is, we haven't seen any gravity situation in the real universe, where we have seen certainly black holes. We've detected black holes, but we haven't seen any gravity situation that would be anything like a wormhole type situation. And so not only do most physicists or astronomers think that they're hypothetical, they just think that certainly the universe near us, the part we can examine well, does not seem to be configured such that wormholes occur. And that was a good question to finish with. And I appreciate your questions on a usual wide range of topics, and we'll be back again in a couple of weeks. Thanks for participating.